different governments have started to decide to reduce the emissions of CO2 per kilometers. And we can see that all these developed countries are trying to regulate these emissions in order to reduce them to some extent. So to address these issues and challenges, we can propose to use alternative fuels such as biofuels, synthetic fuels, but also introduce new engine technologies. So for ground transportation, diesel engines have been very popular. They have higher thermal efficiency than gasoline spark ignition engine. So we can expect that they will still be used in the future, although the sales have decreased significantly in Europe. Anyway, whatever the technology, these are significantly contributing to the emission of carbon dioxide, and also concerns with environmental with emissions of pollutant in the atmosphere and global warming are growing. So biofuels derived from biomass may be considered sustainable, useful, if sufficient quantities of plants can be grown. Also, if a fair carbon balance is achieved, if low N2O emissions are achieved, and if it doesn't compete with food production. Therefore, beside the first generation biofuel, one can propose second and third generation biofuel from non-edible feedstock, like jatropha oil or biomass residue or algae. Already first generation biofuels are mixed in diesel fuel to produce what we call a biodiesel mixture, composed of monoalkyl esters with long carbon chain from fatty acids. They are obtained from renewable lipid feedstock, mostly vegetables, but eventually from animal fat, waste, and algae. So they could be useful to reduce the emission of fossil carbon oxides, but also PAH and soot to some extent. So these alkyl esters, fatty acid methyl ester,
Professor Dagaut, I think we lost you.
Yeah, I am back. I have turned off my camera so that the traffic will be easier, probably.
Sure, perfect. Please continue.
So we can synthesize these alkyl esters from triglycerides, so vegetable oil, for example, with an alcohol in presence of a catalyst. And then you get these esters and glycerol as a byproduct. The composition of oil is changing from one plant to another. And I show on this slide the kind of differences that we have. So, for example, rapeseed, which is very popular in Europe, is mostly composed of C18 and C22 carbon chain, whereas sunflower, which is more popular in the southern part of Europe, is mostly composed of C18 oil. And also insaturation can vary very much from one kind of oil to another one. And we have fully saturated methyl esters derived from these vegetable oils. So 16 carbon atom, and 0 means no double bond on the carbon chain. Same thing for methyl stearate, and for methyl oleate. You can see that there is one double bond somewhere in the molecule. For methyl linoleate, there are two double bonds, and for methyl linolenate, there are three of them. So these number of double bond will have an effect on the fluidity, but also on the tendency to produce particulates. So these are not very complex chemical structure, but still they are much more complex than, let's say, one decade. Therefore, if you want to design some chemical kinetic reaction mechanism to represent the oxidation of these fuels, it's worth proposing some simpler mixture, which we call surrogates. Otherwise, the kinetic reaction mechanism will be really huge, that as those proposed by Lawrence Livermore National Lab. So the second kind of biofuel of interest is ethanol. Ethanol is produced from biomass using different chemical processes. It's an attractive renewable fuel. It is today mostly used in spark ignition engines, but its use in diesel engine could be also of interest. The problem is that it has a very low Cetane number because it has a very high octane number, which hampers low temperature auto-ignition. In other words, it's very difficult to auto-ignite. Also, the solubility of ethanol in petrol-derived diesel is very limited, which induce some problems with fuel stability. But there is an increasing interest for using reformulated diesel fuel composed of ethanol, biodiesel, and petrol-derived diesel fuel, where biodiesel can act as a co-solvent for increasing the solubility of ethanol in the fuel and prevents phase separation. Other alcohols are of interest, like butanol, but also methyl butanol isomers. So on this table, I tried to summarize the different kind of biofuel, second generation biofuels, and what can be their use. So for alcohol, it's mostly interesting for automotives because alcohols, as the other oxygenated fuel, contains oxygen, and therefore you are carrying mass in the plane, which is not useful. Therefore, people are not very much inclined of considering these oxygenates for aviation application, but mostly for automotives. So esters, methyl esters, ethyl esters can be considered. Also, furanics are of interest, although some studies have demonstrated that their combustion can produce some new pollutants, which could be a problem. And finally, there are people also hydrocarbons derived from biomass, like terpenes, which are naturally produced by vegetation, but also farnesene, which is this complex long chain and branched hydrocarbon. So all of these are of interest, and these particularly are more interesting for aviation applications. So here we performed experiments in jet reactor over the pressure range of 1 to 10 atmospheres for the oxidation of alternative fuels and surrogates. But also we looked at the chemistry of oxidation of intermediates, for example, aldehydes, which are formed during the oxidation of alcohols, and that over a range of equivalence ratio from fuel lean to fuel rich, and over a range of temperature which cover both the low temperature chemistry, the cool flame chemistry, and transition to high temperature. We developed detailed chemical kinetic reaction mechanism based on these experimental results, but we also use data coming from other devices like shock tubes and flames. And I will show you some example. So the experimental facilities that we are using are several. As I mentioned before, we use jet stirred reactors. We also use sooting flame, pool fire experiment, smoke point apparatus, derived set and number apparatus, and internal combustion engines. So in jet stirred reactor, we measure concentration profiles. Here we collect soot and pH and try to delineate reaction pathways to explain what we observed. Same thing here with a pool fire. Smoke point is measured with this device. It is used together with this set and number machine to propose some surrogates which can represent a real fuel in terms of emission of soot and auto-ignition properties. And finally, with engines and rapid combustion machines, we can measure pH, we can measure some intermediates, and also when we operate with an engine in FCCI mode, we can study the kinetics of ignition, and particularly sensitization using some oxidizers which are injected in the engine. So what this jet stirred reactor experiment looked like? So it's a small reactor, only 30 cc, 4 centimeters in diameter here. It has 4 injectors, and these injectors have jets which are opposed one to the other. So we have a equatorial circulation here and one crossing it. So this is provided rather good homogeneity inside the reactor. We can operate up to 40 atmospheres because we calibrate the pressure inside and outside the reactor. This reactor is made of fused silica. So we feed the reactor with the different reactants, and they are highly diluted by nitrogen. I will show you on the next slide how things are flowing. So we are achieving macro mixing conditions, and the thermal homogeneity of the reactor is rather good. It is controlled by moving the thermocouple along the vertical axis of the reactor here. And most of the time we are using a high purity reactant for these experiments. So you can see here how we feed the reactor. So we have a quartz capillary here where we send the fuel highly diluted by nitrogen, and outside this capillary, but in this extension tube here, we are sending oxygen and nitrogen. They mix together in this small volume here, flow through the 4 injectors, and finally reach the reactor itself. It is heated from outside and temperature control, and we verify the temperature gradient here and take sample along the vertical axis of the reactor. Samples can be sent to different analyzers, online infrared spectrometry. We have also gas chromatography with flame ionization detector, mass spectrometry, and also thermal conductivity detector. And we can also bubble the gases which are exciting the probe in cooled acetonitrile. And this solvent is excellent for trapping the chemicals which are formed during the oxidation of the fuel, and I will show you some results later on. So at the exit of the probe, we bubble this sample in cooled acetonitrile, and then we can send it to a high resolution mass spectrometer, either directly or after separation by liquid chromatography. And we can do the same with an engine, and we can do the same with a rapid combustion machine. I will show you example of results later on. For the modeling, the chemical kinetic modeling, we try to use accurate kinetics, thermochemistry, and transport data. We use inputs from theory, measurements, but also estimation based on analogy of similar reactions to propose kinetic parameters. We need